This is the 6th lecture in Signals and Systems, and the title of today's lecture is Convolution, Invertibility, Causality and Stability. The topic of convolution we had already started the previous day in the context of discrete time signals and systems, and we showed that if x of n is an arbitrary input to the system and h of n its unit impulse response, then the output y of n is given by the convolution of x of n and h of n, where the convolution operation simply stands for a summation which is xk h of n minus k, k going from minus infinity to plus infinity, or its equivalent which is x of n minus k, h of k, k goes from minus infinity to plus infinity, and this is valid for time invariant systems. Of course, the system has to be linear. For a linear time invariant system, discrete time signal input, the output is given by this particular relationship, and I keep on repeating this because you must get it by heart. Convolution. We now look at convolution in the continuous time domain, in CT, systems and signals, continuous time systems and signals. And we shall use a very similar kind of argument, namely, let us say that we have an LTI system, linear time invariant system, whose impulse response is h of t, that is delta t leads to h of t. Then, because of time invariance, if the input is shifted by tau, delta t minus tau, then the output should also be shifted by the same amount, h of t minus tau. This is a consequence of time invariance. Then we bring the linearity into consideration. We multiply both sides by a constant, that is x of tau d tau. We multiply both sides by a constant x of tau d tau, and therefore we get delta t minus tau should lead to x of tau h t minus tau d tau. And the next thing that we do, what principle is being employed here? This is homogeneity. That is, if the input is multiplied by a constant, the output must be multiplied by the same constant, homogeneity. Then we apply superposition, the other part of linearity, which means that we integrate the left hand side from minus infinity to plus infinity, and we integrate the right hand side also from minus infinity to plus infinity. So if this integral is the input, then the output should be equal to this. Now if I write it again, integral minus infinity to plus infinity, x of tau delta t minus tau d tau, this should lead to integral minus infinity to plus infinity, x of tau h of t minus tau d tau. If you look at the left hand side, you notice that because of the peculiar property of the delta function, this function exists only at t equal to tau, or tau equal to t. Tau is the running variable now, tau equal to t, and therefore the left hand side can be written as x of t multiplied by integral minus infinity to plus infinity delta t minus tau d tau, which is unity, and therefore the left hand side is simply x of t, and therefore if x of t is the input, the output must be equal to y of t, that is y of t is minus infinity to plus infinity x of tau h t minus tau d tau, which simply states that if you know the impulse response of the system, that is h of t minus tau, then you can find out the response to any arbitrary input x of t. And formally it is written as y of t equal to x of t convolved with h of t. The same symbol is used, a star between the two signals. One is the applied signal and the other is the impulse response. And in the continuous time domain, the convolution is defined in terms of an integration, whereas in the discrete time domain it is a infinite, double infinite summation. In the continuous time case it is x of tau h t minus tau d tau, and if you make a change of variable, it's very easy to show that you can either delay h or you can delay x. In other words, it is the same as minus infinity to plus infinity, x of t minus tau h of tau d tau. It doesn't make a difference, which in terms of mathematical operations simply means that the convolution operation is commutative. That is, whether you convolve h of t with x of t or x of t with h of t, it doesn't matter, it's commutative. And by applying the definition, it's very easy to show that it is also associative. That is, if you have to convolve x of t with, let's say, two of them, h1 of t star h2 of t, then it doesn't matter what you do first, whether you first convolve x of t with h of t and then convolve with h2 of t, or you convolve, let's say, h1 and h2 and the result you convolve with x of t. So it is associative. Convolution is also distributive. That is, if x of t is to be convolved with the sum of a number of functions, 2 have been shown, then it is equal to x of t star h1 of t plus x of t star h2 of t. That is the distributive property of convolution functions. We have shown with 2, it can be applied to more than 2. Exactly like the discrete time case, you can make a physical interpretation of these operations, that is commutation, association and distribution. Commutation simply means that in a cascade of systems, the sequence in which you cascade is not important if the systems are linear and time invariant. Association means that you can first find the output of one of the systems, convolve it with the next, or you can do it the other way around. That is, you can juggle the subsystems and then go on computing the output one by one. Distributed simply means that the two systems or three systems or any number of systems are in parallel, and what you do is you convolve the input with each system and then simply add the individual outputs. Exactly as in the discrete time domain, you can have a graphical interpretation, which is sometimes the most useful technique for evaluating continuous time convolution, x of t h of t minus tau d tau. You can of course evaluate this analytically if x of t and h of t are given analytically, but most of the time it is more instructive to evaluate this graphically, and we shall illustrate this graphical procedure with the help of an example. The example that we take is, we have an x of t which is a gate function, that is, it is a u of t minus u of t minus t. The duration of the gate is capital T. X of t equal to ut minus u of t minus t is simply a gate function which exists at the value 1 from t equal to 0 to t equal to capital T. This is the function x of t. It's a gate. let's consider the impulse response h of t to be a ramp, that is a linearly rising waveform between let me use a different color, between let's say 0 and twice t, 0 and 2t. Let's say this is my h of t. Alright, what we have to do is to convolve this with the function that I showed. Let me draw this also here. This is capital T somewhere here, then it is this. This is my x of t and this is my h of t. That is, h of t is equal to, it exists between 0 and 2t, and therefore we first use a gate ut minus u of t minus 2t. This is the gate, then we multiply by t. Alright, that is in the range 0 less than equal to t less than equal to 2t, the function increases linearly, rises up to 2t, then it falls down to 0. Alright, we have to convolve h of t with x of t, and we proceed in an exactly similar manner as we did in the discrete time case. What we do is we take h of t. Let's see the mechanism. You first plot x of tau versus tau. Recall that the convolution is simply minus infinity to plus infinity, x of tau, h of t minus tau d tau. This is the convolution. So in step number 1, what you do is plot x of tau versus tau. You see, we have to evaluate this integral. So what we do is we plot x of tau versus tau, then we plot h of tau versus tau. Well, these two are given. Alright. The next step is flip it over, exactly like the discrete time domain. That is, plot h of minus tau versus tau. And then you advance or delay the h of minus tau plot. That is, you plot h of t minus tau versus tau. You see, as far as this plot is concerned, small t is a constant because the variable is tau. Alright. Once you have these two pictures, that is, one is x of tau versus tau and the other is h of t minus tau versus tau, then you multiply the two, x of tau and h of t minus tau, multiply the two and find out the area under the multiplication, under the multiplicand. That is, if you multiply these two, find the area under the plot of x tau h t minus tau versus tau. It is that area which will give you y of t. Alright, integration of a function multiplied by d tau from minus infinity to plus infinity means the total area under this scale. It is that area. It is sometimes easy to find out this area graphically rather than analytically. Did you have a question? Now let's do this example. These are the steps, and in most of the cases it is more convenient to do it graphically because things become absolutely clear. Let's see our h of tau. Let's proceed with this example. Our h of tau was this. It is unity 0 to unity in the range, no, I beg your pardon, in the range 0 to 2t it rises linearly, and therefore this amplitude should be 2t. That is correct. This amplitude is 2t. Now if we flip it over, that is, if we plot h of minus tau versus tau, the same tau, then what we will have is simply this. This level is the same. This will be h of minus tau. that is with 0 as the pivot, the vertical line is the axis, we turn it around. So this is h of minus tau. And then what we do is we find out h of t minus tau, which will mean that the whole waveform shall be shifted to the right or to the left depending on the sign of t. If t is positive, then it shall be shifted to the right. To the right. If t is positive. Now what is the argument? H of minus tau, this is the origin, tau equal to 0. At tau equal to 0, this is 0. Now if I write h of t minus tau, it should be equal to 0 at tau equal to t. And if t is positive, naturally the curve shifts to the right. And therefore, a typical h of t minus tau shall be like this. The violet curve, where this value, this axis, this abscissa shall be equal to small t, because at tau equal to t it becomes 0, and this shall be small t minus 2 capital T. That is correct. And as we vary small t, the overlap between this, and you recall my x of t was simply, x of tau was simply a gate like this. The figure has become complicated, so let's take it to the next figure. Let's draw it again. I want to show a typical h t minus tau. This is h t minus tau. This is small t minus 2t, and this is small t. And my x of t, x of tau versus t is like this. This is tau. This is x of tau. X of tau versus tau is this, where this amplitude is 2t and this amplitude is 1. So, as this triangle moves to the right, the overlap or the non-zero region of the product x of tau and h of t minus tau, that varies. The range as well as the amplitude, and therefore the area under the overlap also varies. And it is this area which determines the convolution, which determines y of t. And therefore y of t varies with t. Now it is quite clear that if small t is less than 0, that is, if this triangle shifts to the left of this vertical line, then there is no overlap, and therefore y of t, the convolution, should be equal to 0. Is this obvious? So for negative t, now you can answer the question that was left in the last class. We had two discrete time signals, both were multiplied by u of n. I left you with the question whether the convolution should also be multiplied by u of n or not. The answer is yes or no. It is binary, so there is 50% probability of getting it correct. Whether you understand it or not, there is 50% probability. The answer is yes. You can see it here that if t less than 0, then there is no overlap between the two, and therefore the product shall be equal to 0, integrand is 0, and therefore the integral shall also be 0. Similarly, if this triangle, this blue triangle, is shifted in such a manner that this edge exceeds capital T, if the triangle comes here, then obviously again the overlap is 0, and therefore t minus 2t exceeding capital T t minus 2t is this point. If it exceeds this point, then the triangle goes completely to the right of the rectangle, and therefore, which means that t is greater than 3t, once again the output should be equal to 0. So the output is non-zero only between 0 and 3t. All the rest of the time axis, the output is 0. Alright, if I plot y of t, then it simply shows that between 0 and 3t, that is all that we have to investigate, because the rest of the curve, rest of the plot is 0. I have at least plotted a part of the response output. Now let's see what happens to this shifting and the overlap. I have a sketch here which shows the situation if small t lies between 0 and capital T. This is small t. That is, the triangle has been shifted to the right by the amount small t, and small t lies between 0 and capital T. Naturally, it is this green shaded portion which is the overlap. And it's very easy to see that the value of this portion is the area of the triangle, half base times altitude. The base is small t, and altitude is also small t, because the slope is minus 1. It is h of minus tau, the slope is minus 1, and therefore half t squared. In other words, in the interval 0 to capital T, yt rises as half t squared. Alright, is this point clear? This is my x of tau versus tau, and this is the triangle, the red one is the triangle, and it is the overlapping portion. In the non-overlapping portion, the product is 0. Either x of t is 0, x of tau is 0, or h of t minus tau is 0. So the y of t, the output therefore, shall rise with small t when small t is between 0 and capital T in a parabolic manner, half of t squared. Is this figure clear? Now, if it goes on shifting to the right, another situation shall arise when small t exceeds capital T. That is, the triangle comes beyond capital T, but the left hand side, that is left hand edge t minus 2t, still does not exceed 0. That is, small t, this edge does not exceed this origin, but this point exceeds capital T. What is the range of small t? Between capital T and twice small t. Let's see what the picture looks like. Pardon me?
Twice capital T.
Twice capital T, that is correct. This is the picture. T, small t lies between capital T and small t. As you can see, for variation I have shown a yellow color. The left edge is a t minus 2 capital T, which has not exceeded 0. It is still to the left of 0, whereas the right point, the end point, small t, that has exceeded capital T. Now the figure that you have is no longer a triangle. The overlap is a trapezium, right? This is the one. The yellow hatched area is the area that we shall be concerned with, and it's very easy to find out this area. What you do is you find out this area. This will be half t squared, from which this is small t, this is also small t, half t squared, from which you subtract the area of this triangle. That will be half cap t minus small t whole squared, and this is the result that you get, y of t equal to this. Alright, so this is the situation between capital T and twice small t. Now you notice that the value for small t equal to capital T can be evaluated either from this expression or from the previous expression, and they should be identical. because it is a continuous curve. And you can easily see that if small t is put equal to capital T, then the value is half capital T squared. That is the value given by the previous expression also. The third situation shall arise when small t goes on to the right and small t minus 2t exceeds the zero line, exceeds the origin. Then the figure will look like another trapezium. Alright, and this trapezium will now be shaped like this. This is the situation for small t lying between 2t and 3t. You see, small t minus 2t has now come here. It has exceeded the zero mark, and the right hand edge, small t, has exceeded capital T. This is capital T. So all you have to do is to find out this yellow area, shaded area, and this is another trapezium with sides of capital T minus small t minus 2t, which is 3 capital T minus t. What is the value here? This value, actually I have not drawn it correctly. This should be 2t. It's not unity. There is a mistake here. Is that clear? This black line is unity, and therefore and this is 2t. They cannot be at the same point. I have drawn it incorrectly. But anyway, what is the value here? What is the value here? T minus small t minus capital T. That is correct. And therefore all you have to do to find this area is to take this multiplied by the average height of the two. And the expression, you can easily verify, comes like this. Now let's put small t equal to 2t. Small t equal to 2t. The two expressions, the expression derived from here and from the previous expression, they should agree. And you can easily verify that they do agree. You also see that if small t is put equal to 3t, if small t is put equal to 3t, what do you expect? The value is 0. You can easily verify that yes, indeed it is so. And therefore, finally, my total output y of t will look like this. Between 0 and 3t, it goes on, let's say t and capital 2t, capital T 2t. You can see, you can find that it reaches a maximum at 2t, and it's more or less continuous between 0 to capital T and capital T to 2t. It's more or less a continuous curve, and then there is a discontinuity. It decays to 3t, it decays to 0 at 3t. This is the total shape of the curve, and therefore the output shall be in the form of a pulse of this particular shape. Now this is an example of convolution, a linear time invariant system. One of the main reasons why linear time invariant systems are so popular in terms of analysis and synthesis is that they obey convolution, and the output is very easy to find in terms of the input, arbitrary input, provided you know either h of n or h of t. Let's next consider characterization of memory systems, memory and memoryless systems. How do you characterize? We have characterized linear and non-linear systems in terms of superposition and homogeneity. We have characterized time invariant and time varying systems in terms of its impulse response, that is h of t and h of t minus tau, or h of n and h of n minus n naught. What about memory-less systems? If you recall, a memory-less system is one whose output, present output, depends on present input only and nothing else. Alright? Can a memory-less system be non-causal? No. You remember what is non-causal? Non-causal is anticipatory. Can a memory-less system anticipate? No. Because its present output y of n, if we take a discrete time system, depends only on x of n. So how do you characterize such a system? Well, obviously, you see, if x of n is a unit impulse, if x of n is delta n, then what do you expect for its output for a memory-less system? It only depends on delta n, and delta n exists only at n equal to 0. So the output cannot exist anywhere else than at n equal to 0. Is that clear? And therefore, y of n in response to delta n, what do we call it? We call it the unit impulse response, h of n. H of n therefore must be, well, what is h of n? H of n exists only at n equal to 0. And any signal, any discrete time signal which exists at n equal to 0 at a single point can be described in terms of the unit impulse, and therefore it must be of the form k times delta n. Is this point clear? That for a memory-less system, if the input is delta n, output must be k times delta n. It cannot be anything else, because there is only one sample at n equal to 0. And obviously the value of k, the constant k, is equal to h of 0, right? K is equal to h of 0. In a similar manner, if we consider a continuous time system,
so can't there be a system in which, suppose there is no signal, x of n is 0, then it gives an output of 1, and when there is a signal it gives an output of 0.
If x of n is 0,
then y of n is equal to 1.
Has to be, for a memory-less system, has to be 0.
So not necessarily, maybe there is something like, it's shorting something. The
So
signal shorts something.
then it is memory, because if it is non-zero, it must have a memory. It must have memorized some part.
It's not memorizing something, say it's just taking it like at that instant itself it's measuring, and say maybe it's shorting a diode or something. If there's a signal, it shorts it, and otherwise it doesn't short it.
You give me this circuit, then I shall explain. Whatever you do, before the input is applied, there cannot be an output. And a memory-less system is an extreme example of this. That is, it can neither memorize nor anticipate. It only lives for the present. That's what most human beings do. They live for the present. They don't anticipate what the future shall be. They don't learn by past experiences. And therefore human beings are mostly instantaneous systems. You give me the example of the diode circuit. We shall examine this and show that it must have memory, otherwise it cannot be so. That is for zero input. A capacitor, for example, well, even if the input is 0, it can store some charge, and therefore it has memory. A memory-less system has to have an impulse response h of n equal to k x of n. In a similar manner, in the continuous time system, CTS, the impulse response by exactly the same argument. For a memory-less system, it must be of the form k delta t. Can you now say what is k? Can you say what is k? Is k equal to h of
Minus infinity to infinity.
K is a determinable constant. If it is indeterminate, then you don't know what the system is. H of t, the indeterminacy of h of t is taken care of by delta t. Unlike the discrete time case, the amplitude of delta t is not finite. Can't you say what k is? In the previous case, we characterized k I'm sorry, I made a mistake here, k times delta n. In the previous case, we characterized k as h of 0. What is k here? Let's call this k prime. What is k prime here? It must be, that is right. That is correct. You see the difference between the two constants? A continuous time memory-less system has a constant in its impulse response, which is given by the total integral of the impulse response for all times minus infinity to plus infinity. Now, under what condition? The purpose of this discussion is to show to you that h of t or h of n, the unit impulse response in the continuous time case or the discrete time case, is adequate for describing the system completely. We have shown linearity, time invariance, we have shown memory or memory-less. Memory-less systems are characterized by its impulse response. Impulse response shall be 0 for every other value of the abscissa except 0 value, the origin. That is, h of n is equal to 0 for n not equal to 0. Similarly, h of t is 0 for t not equal to 0. Now let's see, we had another characterization, inversion of a system, invertible or non-invertible. And you shall see that this is also characterized in terms of h of t. Suppose we have to bring variety into experience, let us say h of t is the impulse response of a given system. Now, in order to make this system invertible, if the system is invertible, then we must be able to find another system called the inverse system, such that the output of the inverse system is equal to x of t. And therefore, if the impulse response of the inverse system is h1 of t, then this must be what kind of a system? Identity system, the combination of the two, because it takes x of t, gives an output of x of t, and therefore this must be an identity system. Now, what does an identity system mean? This is a system of cascade of two systems having impulse responses h and h1. So what is the relation between h and h1? The convolution of these two should be equal to delta t. Why? Because after all, any system whose impulse response is delta t, what is the output to x of t? It is x of tau delta t minus tau d tau. And what is this equal to? By the property of the impulse function, it's equal to x of t. And therefore, identity system is one whose impulse response is equal to delta t. Which also means that, let's put it in a different form. If x of t is convolved with delta t, then it is equal to x of t. Not 0, it's equal to x of t. Any function convolved with an unit impulse is simply equal to that function. Suppose I convolve, going a little out of the track, suppose I convolve x of t with delta t minus t naught. What will this be?
0.
Be careful. Say it again, what is this equal to? No,
x of t minus t.
That is correct. This is the characteristic, x of t minus. You just apply the definition and you see that it takes the value of x of t minus t0. Alright. Now, that's about convolution. So, the problem of determining whether the system is invertible or not in the continuous time case boils down to determining if there exists an h1 of t such that, well, the question is, let me write it down, is S invertible? This question is equivalent to, does there exist a h1 of t such that h of t convolved with h1 of t equal to delta t. It's not a very simple question to answer. You might have to do quite a bit of calculation to be able to answer this question, but in very simple cases there are simple answers. For example, if h of t is equal to delta t minus t naught, what does it mean? It means that the system is a simple delay. That is, you apply delta t, look at the physical picture, you apply delta t to the system whose impulse response is h, delta t, and all that comes out is delta t minus t0. That is, the unit impulse is simply shifted to the right or to the left depending on the sign of t0 by the amount t0. Now the problem is to bring back delta t. How do I do that? If I connect it to a system whose impulse response h1 of t is delta of t plus t naught, then obviously I have put it back on the rail to its original position. So the system obviously is invertible. If a system has an impulse response delta t minus t naught, then the inverse system has an impulse response delta t plus t naught. There is a problem here. If t naught is positive, what does it mean? It means that you have advanced, you have anticipated, and therefore the inverse system is non-causal. Alright? Causality is not part of invertibility. In other words, an invertible system may be causal, may be non-causal, and therefore causality should not be brought into consideration while finding an inverse system. The answer to the question, does there exist an h1 of t such that ht convolved with h1 is delta, is yes in this particular case. Suppose I have, let's take another example, let's take a discrete time system. Let's say hn is un. Alright, a discrete time system which is characterized by this, unit impulse response is equal to the unit step. Is this invertible? To answer this question, let's find out what is y of n. Y of n by convolution is given by x k, an arbitrary input x of k, multiplied by h of n minus k, u of n minus k, where k goes from minus infinity to plus infinity. Alright, this is my convolution relationship, where instead of h of n minus k I have written u of n minus k, because h of n is u of n. Alright, now u of n minus k is unity when its argument is greater than 0, that is n minus k greater than 0, which means that k is less than n. So the upper limit infinity should now be modified to small n, because beyond n, if k is greater than n, then the function is 0, and therefore the upper limit can be modified to small n, and this is what we get, xk. I can omit u of n minus k, because u of n minus k for k between minus infinity and small n is 1, and therefore the product is 1. Now therefore my relationship is y of n equal to xk summation xk k equal to minus infinity to plus n. The question now is, the question that we ask is, does there exist an h1 of n such that h of n convolved with h1 of n is delta n? This is the question. Does there exist? This is the question. Now, instead of answering the question directly, that is taking the convolution and trying to find whether delta n exists or not, why don't we look at the input-output relation, that is y of n equal to k equals minus infinity to plus, no, not plus infinity, n x of k. You notice that if I input an x of n, I get an y of n, and if there exists an h1 of n, that is if the system is invertible, then by applying h1 of n, I should get back x of n. So the question now can be reframed like this. Can I, from a given y of n, can I recover x of n? That will answer the question, isn't it? And you can see that y of n minus y of n minus 1 is simply equal to x of n. And this is totally implementable. You take the present input, the present output, y of n, and a delayed output. That is, what does a delayed output mean? It's previous output, right? So, y of n and y of n minus 1, and simply subtract one from the other. This must give you x of n. In other words, this will then be an identity system, and we say the system is indeed invertible. Next. Alright, so what have we done so far? We have said linear, non-linear, time invariant, TI, time varying, memoryless, and what did we discuss now? Invertibility or non-invertibility. Each of these can be characterized in terms of the impulse response. Let's look at causality. Causal or non-causal. And for characterizing causal or non-causal system, all we do is appeal to common sense. And the common sense is this. Our purpose is to show that h of n is still a characteristic. It still characterizes causality, causal or non-causal system. H of n or h of t, as the case may be. So we apply to common sense. We say, suppose the system receives a delta t. Alright. Now, can the output appear before delta t shows its existence? Can h of t, delta t is input, the output is h of t. Can h of t be non-zero before t equal to 0? If the system is causal, that is, if the system is non-anticipatory, then obviously at negative time it cannot anticipate that an impulse shall appear at t equal to 0. And this simple argument shows that a system, a continuous time system, is causal if and only if ht equal to 0 for t less than 0. Alright, because ht is the response to a unit impulse, and unit impulse appears only at t equal to 0. Therefore, ht equal to 0, t less than 0 describes a causal continuous time system. In a similar manner, we are not saying anything about t greater than 0. How come? Well, the response can be delayed. If it is a memory system, then h of t can be non-zero for t greater than 0. Apply an impulse, for example, to an RC circuit. Apply an impulse. The capacitor charge rises instantaneously and then decays. Alright. So h of t can be 0 for t greater than 0, but not for t less than 0. Because the system cannot anticipate. In a similar manner, for a discrete time system, a causal discrete time system is characterized by the fact that h of n equal to 0 for n less than 0. Alright? So it describes h of t or h of n, also describes causality. Finally, we look at stability. And stability shall be a bit of involved consideration, because it does not it doesn't come out by common sense. We have to do a bit of mathematics. But let me recall my definition of stability, or the stability that an engineer is concerned with. The stability that we are talking of is BI/BO. That is, if x of n for a discrete time system, if x of n is bounded, it can be positive or negative. If x of n is bounded by, let's say, L, which is less than infinity, that's what binding means. It is bounded means it has the maximum value that it can take, the maximum magnitude that it can take is capital L, which is finite. Then y of n, which could be positive or negative, is also bounded, less than equal to, this bound may be quite different from capital N. It could be 10,000 times capital N, but it must also be less than infinity. And if this is satisfied, then we say the system is bounded input, bounded output, or it is stable under bounded input. No, I'm sorry. It is stable in the BIBO sense, or bounded input, bounded output sense. There are other kinds of instability, which you shall come across later. But for a physical system, mostly what you are concerned with, BIBO, and we shall show next time that stability can be very excellently described in terms of h of n or h of t. But this will form the discussion of the next lecture.